So hi everyone. I'm Roni from Nexar, and I'm going to present the latest world model that we build. So first, few words about Nexar. So at Nexar, we operate the largest dataset of driving, the open dataset that exists in the world. We have more than 10 billion miles that we collect. We have more than 98 coverage percent of the US road. And we do it with more than 350,000 agents that driving in the road using our camera. And we collect a lots of corner case that happened in the real world. And let's see a few examples. Now, all those videos are real videos that we collect using our data pipeline. So we have models that's running in the camera. The models are able to detect corner cases while they happen, like hard brakes, harsh acceleration, sharp cornering, and etc. And during the last 10 years, we collect more than 70 billion cases, 70 million, sorry, 70 million cases of edge cases on the road. And we have the entire long tail. So everything that we can imagine, we have the video happened, and it's a real video. So we decide to build world model that we're able to analyze and understand the physics of the road using our videos. And when we try to build a world model, we experiment a few different approaches. So the first and classic approach is autoregressive based model. This is how most of the video models are working. And the idea is to try to predict the pixels of the next frame by masking part of the pixels and predict what's about to happen. Now, the problem with that is that the model going to lose a lot of energy trying to analyze and understand the exact texture and shape and colors of the video, and sometimes miss the physical context and the actual meaning of the video. So this is why we focus on VJEPA. And VJEPA is the architecture that was, this is Jan LeCun big dream. It's a model that learns on the latent space. So the model doesn't learn on the pixel space, the model learns on the latent space. So first we encode the video into vector representation, and then we do all the masking, demasking on the latent space, on the vector representation space. And with that, the model should be much more strong with physical understanding, and the model should learn the exact context of the video and not just the texture and stuff like that. So we do it. We took the VJEPA model that was released by Meta, and we fine-tuned the model on large scale of our data, around 20 millions. It's not all of the data. It's we collect a lot of GPUs to do the training, and 20 millions was enough. And then we trained three sizes of VJEPA, 300 million, around 90 million, and 20 million. Then we was able to use the world model that we build for a bunch of different use cases. The first use case is BADAS. This is the model that I'm going to focus on the presentation. And the model was designed to give you previous alert before the some danger that's about to happen, like collision or something else that's going to happen in the road. And we can also use the same embeddings the same world model for embeddings, like search, retrieval, and video understanding, and also for trajectory. So as I said, this presentation will focus on BADAS, our collision anticipation model. So to build BADAS, we just we would take our world model, our representation model that we build, and we just connect to it attention head to classify if in 2-3 seconds from now it's about to be collision or not. So we released BADAS 1.0 a few months ago, and it was a state of the art for this type of task of collision anticipation. And few weeks ago, we released BADAS 2.0 that was trained on large scale of data, around 2 million clips. that we manually annotated if it's danger clip or not. Now, the way that we annotate the data for BADAS 2.0 was focused on two main vectors. The first vector was to use BADAS 1.0 as an active learning model to scan our entire corpus, find a lot of videos that are candidates for collisions or dangerous situation, and then use human in the loop to verify it and add the video to the training data. This was help us first to find a lot of new positive, but also to find a lot of false positive from BADAS 1.0. False positive usually means something that is weird, is unusual, but not necessarily means that about to be collision. And the second vector was to use our Atlas platform. And our Atlas platform is a platform that you can search in free text for any corner cases that you want. It's also based on our world model. And we just use agentic flows to collect a lot of different examples like animals on the road, different weather, different light condition, and etc. So let's see few examples of BADAS 2.0. So as I said, BADAS 2.0 is the latest model to anticipate collisions, and it's currently state of the art. It's beat BADAS 1.0. And behind the performance, BADAS 2.0 has two new features. The first new features, and it's just an emergent feature, we don't train the model for that, is the attention maps. So we can analyze the attention maps of the model, and with that we get kind of segmentation for free, and we can understand for which part of the video you should be careful, and on which part of the video the model was focused while it generates the alert. And the second part is reasoning. And when I say reasoning, it's mainly about explainability. So we train the educative part, and in a few slides I will explain how. We train the educative part that generate free text description about why the model make the alert. So right now we don't adjust information that something dangerous about to happen. You can also understand why in free text. So as part of BADAS 2.0, we build, as I said before, 3 sizes of the model. BADAS 1.0 was just the large version. And with BADAS 2.0, we build 3 sizes of models. And those 2 small models are can be fitted into Jetson-like devices and can run on real time, even on our camera or on any other edge device. So here you can see the performance. We can see that the model is able to generalize not just for our data, but also for other existing data set and existing open benchmarks. And as part of the analysis that we made for BADAS 2.0, we create new benchmark of long tail. All of those cases was collected by our pipeline, and we create dedicated benchmark for cases like animals on the road, pedestrian, or other corner cases. And we can see that although that BADAS 1.0 was pretty good to make the alert on those cases, BADAS 2.0 is achieve performance of almost 100%. We can see that I mentioned before that we choose to use VJEPA, but we also try to use Cosmos, the world model from NVIDIA. So we can see it here. We tried the vanilla version of Cosmos, Cosmos Reason 2, and it was not perfect, and it makes sense because he was not trained dedicated for that. But then we tried to fine-tune Cosmos. So we can see it here. We have the Cosmos BADAS model, and Cosmos BADAS model is Cosmos that was fine-tuned on the same corpus as BADAS 2.0, and still we can see that the VJEPA-based model, our BADAS achieve better performance, and the size of the model is much smaller, around 300 million versus 2 billion. And also the 2 small models are also perform better than Cosmos, although the sizes is more than 10x smaller. Here we can see a few examples of the explainability part. So here we can see a few examples of real videos and real alerts that the model made. And we can see the heat maps. So we can see like pedestrian, cyclist, animals, or another cases. And we can see on each case the exact object that you should be careful. And again, we just get it for free by analyzing the attention map. Now let's talk about the reasoning part. So the way that we trained the reasoning model was first we extract the attention maps of BADAS, and then we convert the attention map into bounding box. Then we create curated data set using human annotators for about 10,000 videos. And we manually create descriptions about why this video is danger and why the model generates the alert. And then we fine tune Qwen. Qwen gets an input, the frame with the bounding boxes, and Qwen generates the description. We use Gemini just for reformulate the descriptions from the human annotators. And now we can see two examples of real videos. With the first video, we can see video of pedestrian. We can see that the model predict that it's about going to be danger. We can see the heat map. We can see why. And then we can see on free text what is the action that you should take and what is the reasoning. And we can see also example of animals. So we can see animal that about to jump into the road. The model predicted from advance, and the model give you reasoning for why you should be careful. Now I want to deep dive into the distillation process. So I said before that we have three sizes of the model. And when the way that we train two small sizes was first train the large model and then distill the two small models from the teacher, from the large model. Now, the interesting part is that most of the learning came from the first stage. So even without distillation, if we just running self-supervised learning VJPA style on the small model and then just use the labels to train the models, the performance was near to perfect. And the distillation was mainly need for better decision boundaries. But if we try to do that without the self-supervision, the performance was almost random. So most of the learning came from the self-supervised part. So after the distillation, the model can run on any edge device like Jetson or Simular, and the runtime of the model is around between 4 to 3 milliseconds, depending on the size of the model. And this is for the model, the inference latency. Now, it's just fun fact that when we make the profiling of the model, because we're using sliding window, we saw that the VJPA pre-process part of from Hugging Face was doing the pre-processing on the CPU, and it took 2 minutes per inference. So we just check what happened inside the pre-processing part from Hugging Face, and we saw that it just do 3 steps like normalization and stuff like that. So we just re-implement them on the GPU, and it dropped from 2 seconds to 1 milliseconds. So it was basically for free. Now, we try and we check the performance of the model on a bunch of benchmarks, as I demonstrated before, and it was able to generalize. And then we check also for few customers data set, and it was able to generalize also. So we check the model on extreme out-of-domain cases, like you're going to see right now. So yeah, even if it's not driving, synthetic videos, drones, forkits, basically doesn't matter. If it's some object that's going to create collision with another object, the model is able to generalize, to make prediction, and to explain with free text why. So before I will finish, I want to show you just a peek for the another use cases that I mentioned before about other downstream applications that we can use the world model for. So this is one example. This is Atlas, our platform that we can search videos. And we can basically type any prompt and find the similar videos that correspond with that prompt, like Ghost in the Road. And here we can see how the model is work behind the scenes. So here we see visualization of the embedding space. And we can see how if we pick specific area like tunnels or sirens or any other phenomena, we can see how the videos that located close to the video that we pick are also with similar visual context. And again, it's just PCA of the space. This is another example of trajectory. And again, we're using here the same world model. So same engine, just different head. And we can see how the model is predict the future trajectory and the present trajectory. And the model can give you guidelines on about which action you should take. And this example is, for example, from NVIDIA AV dataset. Again, not Nexar dataset, but still the model is able to predict the next step that you should take. The last example is for Carla, and this example is closed loop. So closed loop means that the model decide what will be the position of the car in T+1. And we can see that even in closed loop, the model is hold without dedicated fine tuning for that. So that's it. And thank you for listening. You can scan the QR and check the models yourself. Thank you.